In this video, we're going to do a little quick intro demo to an R script and just sort of play with the idea of variable. I'm going to try to make it practical, but I don't know if it really is practical because I'm going to do a problem, I guess I would say is from biophysics, and I'm not a biophysicist. But let's try it anyway. So we want to look at the resistance to the airflow in trachea, sort of somehow connected to sort of how hard is it to breathe. And I sort of gave a number of websites of reference here. But we want to use this formula for the resistance to a particular kind of flow, laminar flow, as opposed to turbulent flow, where the resistance is 8 times this viscosity given by the letter eta times L, the length of this tube through which the fluid is flowing, and then divided by pi r squared, the radius of this tube. Okay. And that is the Poiseuille equation, and sometimes the Hagen-Poiseuille equation. All right. So that's what we want to do. We want to assign variables for eta, L, and R, and then calculate this formula, and then play with the idea of variable. Vary the values and see what happens to the resistance. Okay. So I want an eta. I'm going to spell it out. And I have a bunch of, so this was for the formula. Here was my value of eta. It's temperature dependent, but this is for sort of normal room temperatures. Sometimes you'll find the eta for, 300 degrees Celsius. So I'm interested in trachea and breathing, so I want sort of room temperatures. 15 degrees Celsius seems reasonable. And they're saying, I'm going to go with this 1.81 times 10 to the minus fifth Pascal seconds. That's, I think, the sort of standard. And here it is kilograms per meter times second in the denominator. And so those are sort of normal MKS physics units. So I'm going to put that in 1.81. And then in computers, e to the minus 5. That's how we do scientific notation. And I'll just enter that, and I'll bring it over here to my environment. Okay, so what is next in this formula is I think the length and then the radius of the tube. So I'm just going to call it L, and this is the length, and the tube we're going to talk about is the trachea. So I think that was my last tab over here. On average, the length of the trachea is 10 to 13. So I'm going to start with the 10 and then go to the 13. And this is centimeters, and I'm working in MKS. So I've got to convert that to meters. So two places. So I'm going to say the length is 0.10. And then the radius of the trachea. And so they have a big study here. Let's say men 20 to 79, 25 to 27 millimeters. Okay. So this is the diameter, and I want the radius. I'm going to have to divide by 2. This is in millimeters. And I want meters, so I'm going to have to move the decimal place 3 places. So I'm going to put in, I think, what is it? 0.00125 for the radius. No, sorry, I might have said too many O's there. I'm going to move the decimal place 3 times, so that would be 0.025, and then I'm going to divide by 2, so 0.025. Or 125. I'll get it right yet. One more time. Half of 25 is 12.5, and then I'm going to move the decimal place 3 times. Okay. So I think I finally have it. I'm happy, I think. And now let's go back to the formula. And there it is, 8. So I'm going to do some capital R. And let me enter those. And in R, it is case sensitive, so I can use small r and capital R as different variables, and it's fine with that. And it was, what was it? 8 times the viscosity eta times the length. And let me be like overly careful. When it has a fraction like this, then I like to put parentheses around the whole numerator and the whole denominator to make sure I'm calculating a numerator, calculating the denominator, and dividing it. It's overkill here, especially for the numerator, but I'm going to do it anyway. So, so there is my numerator, 8 eta L, and my denominator was uh, pi r to the fourth. And pi is, so 8 is of course understood in R. Pi is understood as pi 3.14, and then all multiplications are explicit, so I have to put in that. And then I have my radius, and that is raised to the fourth power. And so then here I am calculating, run that, and so here is the resistance. So even though this eta seems so small, I had also a small radius in the denominator and raised to the fourth, so I ended up with a fairly significant resistance here. Okay, and then just to play the whole idea of variables is that the values can vary. So let's change it a bit. So let's go for like somebody who's taller who might have 12 centimeter length. And then what about the radii? What was like a small radius? The lower limit of normal for both dimensions is 13. Let's do men. So 13. So divide that in half is what, 6.5, and then move the decimal place. So that would be 0.0. Let's just go 0.006. Let's go for, let's do 6.5. Okay, so that was the 13. So now before we had 188, but now we're going to change L, change R, and recalculate, and it is now we're up into 3,000. So we went from 188 or something to 3,000 by that restriction. Because this, you have that radius raised to the fourth, a change in the radius is like a huge difference. That's it. I have no idea if these values make any sense. I'm more just interested in demoing R and playing with variables. So we had a bunch of variables and gave them values. This was the sort of computer version of scientific notation with the E, enter the formula, and then the idea of variables, that they are indeed variable, that we can change them. So the pi, the eta can change. It depends on temperature. But I didn't bother changing that one. But I just talked about, I don't know, different from human to human, different bodies. So I changed the L, I changed the R. That's it for this one. Thanks for your attention.